We'll be discussing the first law of thermodynamics, and hopefully by the end of this lecture, you will be able to, 1, understand what the first law of thermodynamics is, 2, be able to understand, have a more conceptual understanding of what energy is, and as a result, understand what internal energy and enthalpy are. We will also be discussing work and heat as they relate to the first law of thermodynamics. We will be discussing a variety of different types of work and how they relate and ultimately become part of the first law of thermodynamics. So, the crux of the first law of thermodynamics is fairly simple, and it is something that you've invariably heard no matter what kind of science background you have. You've probably heard at some point that energy is conserved. And the first law of thermodynamics comes here in its support, that basically just states that energy is conserved, that energy cannot be destroyed and energy cannot be created. That's really all that there is to it. Of course, there's a lot of mathematical intricacies that go into it that we can apply to a variety of different scenarios. But really, if you understand the idea that energy must remain the same, then you really understand the conceptual understanding of what the first law is. Now, let me ask you a question that may not even occur to you. What is energy? I mean, we use that word all the time, but what is it? So, you may think that you have an intuitive understanding of what energy is. And when I was first asked that, I thought that, for sure, I understand what energy is, but it's just energy. But then I really started thinking about it, and understanding what it is tangibly is kind of difficult, because I can't hold energy, I can't really trap energy to my liking and understand what it means. And really, if you look it up in a dictionary or something, you won't see anything that gives you a tangible definition of what energy is. You know, like if someone asks you, what is an apple? Well, an apple looks like this, and it tastes like this, and it comes from this tree, etc. What is energy? So the short of it is that we don't have a tangible definition for it, and we have to resort to what we know. So to kind of restrict energy and see how it interacts to be able to explain it. And the reason is, you know, we've come to existence and we understand that there's energy around and we use it and it happens. So we had to kind of find a way to define it, and we can measure it and we can use it. So what is it? So the crux of that is that if I have, let's say, a box, okay, and I don't allow anything to go in or leave that box, okay, so I restrict that into a closed box, we call it a closed system. No mass comes in or out, okay, so, you know, maybe like a bottle that you capped or something like that, okay. What we say energy is its ability of whatever's inside that box to do some sort of work for me, or to release some sort of heat to its environment, okay? And those two are the two forms of energy that can cross the boundary of a closed box. So what we're going to do, we're going to see that there is this thing called work, W, and another thing that's called Q for heat. These are the only two forms of energy that can leave a closed box, okay? If I had this closed box in complete isolation, you know, in the depths of space between galaxies where nothing occurs, and this is completely vacuumed, whatever energy I have inside this box is trapped there forever. It cannot leave, it will stay there, it won't leave. It's an isolated system, it's an isolated box. There is no interaction with its environment, it's going to stay in there. So the idea is that the energy of an isolated box stays constant. The energy of a closed box, meaning that I have stuff around, can interact with stuff around through the boundaries of the system, through the bottle. The water can interact with the outside air, either through heat or through work. That's kind of the only definition we have for energy. Okay, and we're going to use this idea for energy, and we're going to see how it becomes useful for us beyond that. Because I promise you, you will have an intuitive understanding for energy. You will have an intuitive understanding for all the things that comprise energy, I hope. So, you probably haven't barely seen, if you took maybe high school physics or even middle school science, you've probably seen an equation that kind of looks, I'm not sure they use this jargon, kind of looked like this. Okay, and I'll explain what that is, but this is the first law of thermodynamics, mathematically speaking, in its most general form. And what this delta means is a change. I started with something, I ended with something, I'm taking the subtraction of the two, okay? So if I had a box and it weighed 10 grams and I put 10 more grams in it, then the change in mass in it will be delta mass, it will be 20 minus 10, it will be 10. So that's what that does, it just takes the final minus the initial. So the change in energy of some sort of something I care about, like a system, like maybe your body, maybe an elephant, maybe a box, whatever it is that you're trying to study, the change in energy of that system is going to be the addition of kinetic energy and potential energy differences. Okay? That's really the most general form of the first law of thermodynamics. And let me explain what these are. So, kinetic energy is the energy of movement, okay? And it does not necessarily mean that you're moving a big, heavy object or ball or something like that. It could be something even small as an electron. Electrons can have a kinetic energy as well. And this is known as stored energy, okay? And you may have seen that too. Now, I have a lot of umbrage with these terms in their essence because they don't really tell people. When I saw this for the first time, I didn't really understand what that meant, because usually when they explain this to you, they talk about that within the context of there's a hill or some sort of change in height, and there's some sort of a ball, and someone comes in and kicks it, and the ball falls down the hill and climbs back up and goes here. That's how I was introduced to it, and I know a lot of physics classes, that's how they start with understanding kinetic and potential energy. And the idea was, before somebody kicked it, it had a high potential energy, then somebody kicked it at the bottom of the hill, it had a low potential energy, and then it went back up again and it had a high potential energy. Here it had no kinetic energy, it's not moving, and then as it is moving, it's got kinetic energy, and at the end it doesn't have it again. I have a lot of umbrage with this because what the heck does this potential energy mean? This ball doesn't know that it could fall. So what is it? Why is it that we have this term called potential energy? It's not, I think it's potential because I know the ball is there, but does the ball know it's there? How can we measure something that is not real? How do we know that there is potential energy? Well, let me show you. There are a variety of types of potential energy. This is known as mechanical potential energy. There's a bunch of different ones, and some of them are more intuitive than others. And so in each one of these, okay, are embedded a bunch of tiny little examples of movement and potentials. Okay, so what we just saw with the ball was, one idea of it was gravitational potential energy, and that is given as this: mg delta z. M is the mass of whatever that ball was, or whatever object you have. G is the gravitational constant, and delta z is the change in height. So the higher the delta z, the more energy I have stored at the top with this marker. Okay? Here it doesn't have as much potential, here it has more potential. But you see, the marker does not know I moved my hand. So I always had a really hard time understanding what that meant. So let me explain to you in a second. Let me just talk about the kinetic energy of the marker moving, or anything moving. We call that mechanical kinetic energy. And this is delta Ke is equal to 1/2 m, the final velocity squared, minus 1/2 m, the initial velocity squared. Okay? And those, if you took some sort of physics in some way, shape, or form, and I think, even if you took something even rudimentary, if you didn't see it in high school, this is something that you probably have seen, or some broad strokes of this version. Okay, this only tells you stuff about a ball going down the hill. There's so many other things that could and do fall within the purview of kinetic and potential energy. So let me show you some examples that I think are extremely more intuitive in what potential means. Okay? One of the most discussed way that you could talk to your father, your mother, your grandmother about energy is to do with eating and exercise. We always talk about that in the popular culture. I exercised and therefore I burned calories. I ate 5 slices of cake, therefore I intook a whole bunch of calories. Calorie itself is a measurement of energy, okay? And so we're basically saying if I eat a whole lot, I will get more energy. If I exercise a whole lot, I will burn it off. That's very, very similar. It's not actually very similar. It's exactly correct to ascribe it to kinetic and potential energy. So let me explain that. When I eat food, okay, the food itself within it has got some nutrient molecules. And my body will take it in, and it won't just use it right away. It has to store it. It has a stored form of it. And if I have excess, not even excess, if I have some sort of energy that I put in, it needs to store it because I'm not continuously eating. It's not like right now I'm eating and eating as I'm talking to you. I eat in some meal, and then I store that energy to some degree, and then I use it until I'm hungry again and I can eat again. So when my body is storing it, it's storing it in what we call a cell, and that cell can then release chemical energy for me to move, and that becomes kinetic energy. So when we eat, okay, we have stored chemical energy. So think of it as like a chemical battery. So I have a cell, and inside this cell I have a bunch of chemicals, A plus B plus C, whatever. And then they react when I want to use them. And when they react, they release chemical energy, and I use that to move. Okay, so my ability to move comes from the idea that I have it stored. Okay? And so now you understand what it means to be depleted, to be tired, is I don't have enough nutrients for me to sustain myself. So I get to the point where I'm too tired, I have to stop, or I have to eat, or I get exhausted, I faint, whatever that is. And that's because I overdid this. I took too much kinetic energy out of my ability to move, and my potential energy could not offset that. Okay? Whereas in the kinetic energy form of it, that's quote-unquote burning calories, and you can use that same equation, and it's not quote-unquote, you are burning calories, you're releasing heat, and you are burning, you're doing a chemical burn, you're actually doing a mini combustion in each one of your cells. So I'm just quote-unquote doing that because that's the jargon people use without really putting thoughts into what that means, but you are actually doing some sort of combustion reaction. You are releasing this chemical energy into moving around, and you can use the kinetic energy equation, the 1/2 mv squared stuff, to calculate the change in kinetic energy for you to move around. Okay, so that's another kind of way to do that. Another great way to think about this is this thing that we all carry around with us in our pockets, and it's a cell phone. When my cell phone's out of battery, well, I used all of it, and then I could put that and charge that into the wall, and I now have extra potential energy before this thing even used itself. It will use itself in some sort of kinetic form. What kinetic form? Electrons moving around. So the electrons can move around, and I can calculate each of their kinetic energy as well. Okay? Another quick form to think about is snapping your finger. When I hold my fingers together, I can feel a tension. This is known as stored energy. I'm storing some sort of energy. Whereas in my other hand, I'm not. It's kind of limp. So here I'm pressing them together. Here I'm not. And so if I'm doing a snap here, you hear nothing. If I'm doing a snap here, you hear a whole lot, because all this energy is being translated into propagating this energy from one molecule to the next until it reaches your ears. Whereas here, I don't have any energy to do that. So that's the idea of stored energy. And I absolutely abhor the fact that people use gravitational potential to explain what it means, because it doesn't really mean much if that's the only explanation you're exposed to. Alright, so that really explains to us kinetic and potential energy. And that's great. And that is the most general form for it. I mentioned before, that if I have a box and I have my system in it, You know, let's say it's your body burning calories or whatever it is. And for me to interact with my surroundings, I have all this potential energy as far as cells go in my body, and then I'm moving around. The only way for me to interact with my environment if I'm in a closed system is through heat or through work, whether something is doing work on me, or I'm releasing heat or absorbing heat, etc. Okay, so this will come in here by way of another equality, Q minus W. Okay, and these are very important forms to discuss energy. Q is heat, and W is work. Heat, when it's less than 0, that means that your system, the thing you care about, releases it. When it's greater than 0, whatever you're studying, it's absorbing it. And work, similarly, well, not similarly actually, when work is greater than 0, when it's positive, your system, whatever you're doing, is doing work. It's imparting useful energy. And less than 0, that means that work is done on it.